Previously, we discussed the CMOS inverter, and we saw that it consists of a PMOS transistor connected towards the supply voltage VDD, and an NMOS transistor connected between the output and the ground. We noticed that when the input is high, then the NMOS will be on and the PMOS will be off. And in this case, when the NMOS is on and the PMOS is off means it works like an open circuit. And when the NMOS is on, it works like a resistance or like a short circuit for now, like for simplicity, which means that the output now is connected towards the ground because the NMOS is on. So the output will be connected towards the ground and the output will be low. So you notice here that when the input is high, the NMOS was on and the output will be low because the NMOS is on. It's connected towards the ground because the NMOS is on, right? So the NMOS is responsible to connect the output towards the ground. The NMOS is responsible to make the output low. On the other hand, if the input is low, we found that the PMOS will be on and the NMOS will be off. NMOS off means open circuit, so the output is no longer connected towards the ground. And when the PMOS is on, this means that the output will be connected towards the supply voltage VDD, and hence the output will be high. So we notice from here that the PMOS is responsible to connect the output towards the supply voltage VDD, and hence it is responsible to make the output high. So from here we conclude something. In the CMOS inverter, the NMOS is responsible to connect the output towards the ground, and the PMOS is responsible to connect the output towards the high voltage. And when the NMOS is on, the PMOS must be off, and when the PMOS is on, the NMOS must be off. When it comes to designing bigger logic gates other than the inverter, we will follow exactly the same idea. So the design of logic gates based on the CMOS family, it consists of two parts. So always we'll have one part responsible to connect the out towards the high voltage VDD, and we are going to call it the pull-up network. Pull-up network. It consists of a network of transistors. All of them are PMOS transistors, similar to the CMOS inverter. All the transistors in the up network responsible to connect the output towards the high supply voltage, all of them will be PMOS, and we are going to call it pull-up network, PUN. Okay, so let's write the abbreviation here, PUN, better. Pull-up network, and they will consist of all PMOS transistors, and they will have inputs, let's say A, B, C. So this pull-up network, it will replace the PMOS transistor here. Here in the inverter, we needed only one transistor. Here, for any other logic gate, for a general logic gate, we'll need a combination, a group of transistors connected in a certain way that we'll discuss in this video. We call it the pull-up network. And similar to the CMOS inverter, we had the NMOS down responsible to connect the output towards the ground. Here we'll have, instead of one transistor only, we'll have a network of transistors. We'll call it pull-down network. And this pull-down network, as an abbreviation, PDN, it consists of all NMOS transistors, and it is responsible to connect the output towards the ground. And again, it has same inputs, A, B, C, for example. So here, any logic gate design based on the CMOS, it will consist of a pull-up network and pull-down network. Pull-up network is responsible to connect the output towards VDD, towards the supply voltage, high, and the pull-down network is responsible to connect V output down towards the ground. Both of them, they have the same inputs. Let's call them for now ABC, the inputs of our logic gate, and the output will be in the middle. The pull-up network consists of all PMOS transistors, and the pull-down network consists of all NMOS transistors. Okay? And this is the basic design for any logic gate that we'll see in this video. We'll see also that in order to design the pull-up network and the pull-down network, we'll need the equation that describes the gate that we need to design. And to design the pull-up network, we have to reach to a standard form, or there is a standard form for the pull-up network. The standard form says that the output must be written as a function of the inverted inputs of A bar, B bar, C bar. This is called the standard equation of the pull-up network. Because in the pull-up network, we always examine the output which sometimes we call Y here. The output will be high, so the output is Y, and it takes a level of V out. So let's call it Y for now to avoid confusion. Because for the pull-up network, we say that the output will be high when the inputs, which inputs are low, because the PMOS transistors usually they work when the input is low, right? That's why we write the equation as the output is high when the inputs are low. So when we write the logic equation based on what we say, the output is high, we write Y equals when the input is low, when A is low, we write it as A bar. So we'll be clear later when we study some examples. This is the standard equation. Anyways, this is the standard equation. We'll understand it later for the pull-up network. For the pull-down network, the standard equation is Y bar as a function of the inputs. Why is that? Again, because for the pull-down network, we say that the output will be low when which inputs are high. Because the pull-down network, it's on NMOS transistors, and the NMOS transistors, they work when the input is high, right? So we say that the output will be low when this input is high, for example. How to write this in logic equation? We write this as the output will be low, we write it as Y bar. When the input is high, we write it as A. So the output here is called Y and the input is called A. And we say that the output will be low when the input is high, we write it like this. Output is low, we write it as Y bar. When the input is high, we write it as A. Right? That's why the standard equation for the pull-down network is that Y bar equals a function of the inputs. While for the pull-up network, the standard equation is that the output will be high, we write it as Y, when which inputs are low, so it's a function of the A bar, B bar, C bar. So these are the standard equations, and they will be clear later when we look at examples. Let's look at examples for the pull-down network. So examples of the pull-down network. For example, if I give you a pull-down network, and we are going here in these examples, we are going to look at the pull-down network only. If I give you a pull-down network that looks like this. Pull-down network that looks like this, A, B. And I ask you to write the equation for this network. What would you say? First, you will say that the output, Y, will be grounded. It will be connected to the ground. It will be low. The output will be low. Let's write it as a statement first. Y will be low if either this transistor is on or this transistor is on. If Q1 is on or Q2 is on. But Q1 is on when A is high. So if A is high, or Q2 will be on if V is high. So or B is high. So we say that Y will be low. Y will be connected to ground if A is high or B is high. How can we write this in logic equation? Go back to the logic circuit course. You can write this equation as Y will be low, you write it as Y bar. Any variable that will be low, you write it as Y bar. If A is high, you write it as A. Or we write it like this, B is high, we write it as B. So we can write the equation of this pull down network as Y bar equals A or B. As you see, it follows the standard form. Y will be low as a function of the inputs, the two inputs A and B. Let's see another example. If I give you a pull down network, of course I'm making these dots here to represent that there will be a pull up network. If I give you a pull down network that looks like this, of course it should be NMOS, right? Then I ask you to write the equation. You would say what? You would say that Y will be connected to the ground, Y will be low, if Y will be low, if. In order for Y to be connected to ground, both transistors, both Q1 and Q2 must be on in order for Y to be connected towards the ground, right? So if both Q1 and Q2 are on, in order for Q1 and Q2 to be on, since these are NMOS transistors, then you can replace Q1 and Q2 on by both A and B are high. So in this case, we can write the equation here. Y will be low, we write it as Y bar will be low if both A and B, both of them are high, we write A and B. So this is the equation for this pull down network. We notice something here. We notice something very important here. That if we have parallel connection, this parallel connection will give you OR, because the output can be connected towards the ground through this branch or this branch. If the branches are parallel, it gives you OR operation. If the transistors are connected in series, it gives you AND operation. So this is the first lesson that we learn. This is the first lesson that we learn, is that parallel connection gives you OR, series connection gives you AND. The second lesson is that there is a standard form for the pull down network, is that Y bar will be written as a function of the inputs without inversion. So the output inverted will be written as a function of the inputs without inversion. Let's take more examples, one more example. So if I give you a pull down network that looks like this, so this is A, this is B, this is C, and here, by the way, we are going in the logic part, only in the logic part, we are going to remove the arrow in the NMOS transistors, and we are going to plot the NMOS transistor just without an arrow like this, and later for the PMOS transistor to discriminate between the PMOS transistor and NMOS transistor. The PMOS transistor usually in the logic part, they put a bubble here, okay, at the gate. They put a bubble. So this is the symbol that we are going to use for the PMOS transistor, and this is the symbol that we are going to use for the NMOS transistor. The symbol without arrows, both of them without arrows. But for the PMOS transistor, there is a bubble at the gate like this. So this is the NMOS symbol that we are going to use, and this is the PMOS symbol. So now we have this pull down network, and we want to write an equation for the output Y. So we say here that the output Y, let's write it directly, the output Y will be low, so Y bar, if this branch is on or this branch is on. So since we have two parallel branches, we have OR operation. So Y will be low if this or this on or this on. This will be on if A is high, so we write A. Or this branch is on and this branch will be on if both B and C are high, so we write B and C. So here, as you see, parallel connection gave us an OR operation. In the first branch, we have A to be high. In the second branch, in order for the second branch to be on, B and C. Series connection gave us AND operation. B and C must be high. So here we saw how to write the equation for a pull down network. Okay, and this is the first step, is to learn the relation between the connection and the equation. If the connection is parallel, it will give you OR. If the connection is series, it will give you AND. If it is a mix between series and parallel, the parallel will give you OR and the series will give you and you can write the equation simply. And then the second lesson is you notice the standard form of the equation. So these are 3 examples on the pull-down network. Let's take some similar examples on pull-up network. So let me remove these and take some examples on pull-up network. So again, we said that the pull-up network will be all PMOS transistors, right? So let's take pull-up network, examples on pull-up network. Let's take the first example, an example that looks like this. And a bubble here, and this is A, this is B, this is the output Y, and then we have a pull-down network here. This is the supply voltage. As you see, the pull-up network consists of PMOS transistors and it is connected towards the high. As we agreed before, it is responsible to connect the output to high. So here we can write it as a statement in the beginning. We say that Y will be high if this branch Q1 is on or Q2, Q1 on or Q2 on. And then we ask ourselves, Q1 will be on if the voltage here, if the input here is low, right? Because this is the PMOS. The PMOS will be on if the input is low. So Q1 is on means A is low. Q2 is on is equivalent to B being low. So now we say that our statement says that Y will be high if A is low or B is low. How can we write this using a logic statement or logic equation? Y will be high, we write it as Y. Any variable that is high, we write it as it is. If it is low, we write it inverted. Y will be high if A is low, we write it as A bar. Or B is low, we write it as B bar. So this is now the logic equation for this pull-up network. As you see, it follows the standard form that the output will be high as a function of the inputs inverted, right? Second thing is parallel connection again gave you what? Gave you OR operation. Next example, if we have a series connection, A, B. So here we say that the output will be high. So Y equals the output will be high if both transistors are on. If both A and B are low. If A is low and B is low. This is how we write it. So we say that Y will be high if A is low and B is low. So this is how we write the equation for this network. Again, it follows the same standard equation. Although the equation says A bar and B bar, so because you are following the standard equation, you put here A and B. Or what appears here is A and B. So don't get confused. This is the confusing part here. So if you follow the standard equation as here, if you follow the standard equation Y as a function of A bar and B bar, then you put on the network, on your actual network, you put A and B because you are following the standard equation. If you are following the standard equation, you put the variables without inversion. All the variables, you put them without inversion if you are following the standard equation. Later we'll see that if it happens that one of the variables doesn't follow the standard equation, for example, if A here is not with bar, so here A doesn't follow the standard equation, right? In this case, you have to invert it here. So any variable that doesn't follow the standard equation, you have to invert it on the figure, which means that you have to use an inverter. You have to use an inverter before it. So you input A, and then you invert it first, and then you input to the transistor. So if there is a variable that doesn't follow the standard equation, this is in both pull-up network and pull-down network. If there is a variable that doesn't follow the standard equation, then you have to invert it here on the circuit. Okay? Let's take another example, similar to what we did with the pull-down network. So this is A, this is B, this is C, this is the output Y, and then the pull-down network. Here we say that the output will be high. The output will be high, so Y equals, if this or this, if this branch is on or this branch is on. So we have an or, something or something. This branch will be on if A is low, so we write it as A bar. Or the other branch is on, the other branch will be on if B is low and C is low. So if B bar and C bar. So this is how we write the equation for the pull-up network there. Again, we learn here, this is easy. If I give you the circuit and I ask for the equation, this is easy. The tricky part is if I give you the equation and I ask you to plot the network. That's why you have to learn the lesson here. That if I give you the equation and I ask you to plot the network, then you have to learn that OR means parallel branches and means series transistors in the same branch. Okay? You have to learn that if the variables follow the standard equation, then you are going to put them here as they are without inversion. If one of them doesn't follow, like this case, if one of them doesn't follow the standard equation, then you have to invert it at your circuit. So these are the lessons that you have to learn. So we'll continue in the next video with more examples where we mix both pull-up network and pull-down network together. See you in the next video.